Welcome. I'm going to do the last homework problem step by step, and I'm going to use the rainbow notes to kind of, show exactly where I'm doing what I'm doing where. All right. So start with a free body diagram. So what we have is a snapshot in time of when I used to pull Wolfgang in the sled. Okay. So I'm going to represent the sled holding Wolfgang with this box. Okay. She pulls the sled horizontally with a force of 30 newtons, blah, 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 blah. Okay, so first thing we need to do is figure out what forces apply. Okay, so does weight apply? Yep, straight down. Okay. Is a surface supporting the sled? Yes, and it's the horizontal. She's pulling it horizontally. They didn't say that they're on an incline, so I'm going to assume it looks something like this, with the normal force perpendicular to the flat ground. Okay. And then there is an applied force, and I'm going to make that go to the right, since that's our default positive direction. Okay. And then finally, there's no strings involved. Well, so we could call this a force applied or a force tension. Yeah, I am okay with either one of these. It really doesn't matter. Okay. And then the friction will be parallel to the surface, opposite direction contact. So the surface is, so there we go. Okay. Just for the sake of simplicity, we need to be clear about which one we're going to do. So I guess I'm going to call it a force tension because I'm going to assume that the sled is being pulled by a string. But again, this is just a name and it's not critical which one we call it. Okay. Sometimes naming matters. Like if you name something a force normal, it allows you to use that normal formula, right? But for tension versus force applied, it's not critical. Okay, step 2, fill in the data. And the reason we do this as a separate step is because we need formulas. So we need to make sure that our forces all have names in addition to numbers. And if you are a little bit sloppy and don't do this in 2 steps, you might not name all these forces, which then makes it impossible for you to document your problem with forces. Okay, so the tension force is 30 newtons. Wolfgang has and his sled has a mass of 20 kilograms. Clearly, he was a little guy back then. All right, and we know that the coefficient of friction is 0.08. Okay, and keep in mind those are, if they are very specific about what the materials are, you might be able to get those coefficients right from here. Okay, so boop-a-doo. All right, we are done with step 2. Step 3, mass is not weight. Do some turquoise. Okay, so they gave us this mass. We're going to use it to find the weight. So the formula is F sub G equals mg. So F sub G is 20 kilograms times negative 9.81. And unlike inclines, we're generally going to say anything upper positive is upper right is positive, anything down or left is negative. But your picture is the ultimate authority, and you can label directions however you want. You can live in a topsy-turvy world where up is negative, but I'm going to do it this way. All right, so if I do the math here, I get that 20 times 9.8 is 196 newtons, and that's negative. Okay, who left their calculator downstairs? Me. Okay, I'm going to circle that so we can find it later. Okay, components. We don't have to do this because there are no components, because there are no diagonal forces. Okay, now I'm going to, and this is a stage people get stuck on, but realize this is the whole point of the free body diagrams, is to do these. So I'm going to do this in red. No, I'm not, because I don't have a red pen. Let's see. I guess I'm going to do it in blue. Okay. All right. So looking at our picture, I'm going to write F net equals MA, and I'm going to do it twice. Once for the X direction and once for the Y. Okay. So in my X direction, from my picture, I can see I have 2 forces. I call those force tension and force applied, and they equal MAX. And he's accelerating, so I'm going to leave this acceleration alone. All right, and then here, looking at this picture, I have normal and gravity equals MAY. it is not accelerating in the vertical direction, so normal and gravity are balanced. Okay, be careful. This is not always going to be the case. If there is a diagonal force, if there is an applied force in the vertical direction, if you're on an inclined plane, normal and gravity are not always the same. Okay, all right, done. And then finally, we're going to actually try to solve our problem. I can tell you right now, I'm probably going to need a calculator for this. So I have to pause this. Okay. Identify unknown and work backwards to solve the problem. Okay, how fast does it accelerate? That's our unknown. We are looking for this. There it is. Okay, so before we can do that, we're going to need tension and force applied. Whoa, I totally did this wrong. It's force tension plus force friction. I completely wrote this wrong. Sorry. Safe place to make mistakes. Yeah, so going back to our picture, I have force tension and force friction add up to MAX. All right. Okay, so I can't solve this yet because I don't know tension or friction. All right. Now, the way these problems go is three formulas. There's the one we got from this direction, the one we got from this direction, and the third one is FF equals mu Fn, and that's off your reference tables. Okay. So if you can't see how to work backwards and solve the problem, what you can do is kind of just start plugging into these three formulas. But I'm going to look at this and say, well, in order to find force of friction, I'm going to need force normal. So I'm going to start here. So I'm going to do this first. Down to black. 1. I'm doing this in black, and then I put it down. I guess this is as close to black as I got. All right. Here we go. So normal and a gravity of negative 196 newtons equals 0. So force normal is 196. Again, force normal is often the same size as gravity. It is not always. That's 1. 2, I can now come up here and find the force friction. So FF equals 0.08 times 196. Okay. And that works out to be, excuse me while I get my calculator. Okay, so when I plug these into my calculator, I get the force 0.08 times 196 is 15.7 newtons. Now, I warned you in another video that this formula will never give you correct sign. Why is that? Well, mu has no sign. Normal tends to be positive. Friction, the way we draw it, often ends up being negative. Okay, so your free body diagram is the ultimate authority on signs. So I need to put in the force of friction is negative because it's down. And I'm going to circle that because it's an intermediate value. And then the last thing I'm going to do is actually calculate the acceleration. So I have the tension force, which is 30 newtons, plus the force friction, which is a negative 15.7 newtons. So it's a little bit like a divided. I'm going to erase it. Now it's a smear. All right, equals the mass, which was 20 kilograms, times acceleration. Okay, so 30 minus 15.7 is what? 14.3. I'm going to drop units. Equals 20A. And I get that the acceleration is 0.72 meters per second squared. And that sign's going to be positive, which makes sense. It should accelerate in the positive direction because the net force is in that. The tension is bigger than the friction. Okay, so there's my final answer. Whew, all done.